Okay, this video is going to be all about the different energy types that we look at in our energy unit and power. So the first type of energy that we're going to go over is probably the most common form of energy, as in the one that you guys are most used to, and that is kinetic energy. So remember, kinetic energy is whenever an object with mass is in motion. So kinetic energy is our energy of motion. Okay? And because it is an energy, it is measured in joules. So the mass here, remember, is the mass of the thing, or if there's multiple things moving. And the V here is just the velocity, or rather the speed, okay, because direction does not matter. Does not matter. Okay? Because energy, any type of energy, including work, is a scalar quantity, which means direction does not matter. Okay? Not too many tricky things about this equation. Just make sure you're squaring the speed and not forgetting the 1/2. A question might ask you to find the total kinetic energy of the system. And when you need to find a total kinetic energy of a system, you just add up all of the individual kinetic energies that might be within the system. So if you have two objects moving, you would just add up the kinetic energies of the two objects. Next one we're going to talk about is gravitational potential energy. So it's important that we clarify that it's gravitational potential energy, because if we just say potential energy, then we don't know what one we're talking about. We have a couple of different kinds of potential energy. So we're talking about gravitational potential energy. So gravitational potential energy, I usually write as PEG. Reference table writes it as UG. We can think of any of the potential energies as work being done by some force internal to the system. So in the case of gravitational potential energy, if the Earth is in our system, then we gain or lose potential energy because of work done by the force of gravity. Okay? So remember, the force of gravity, or work rather, is Fg times the displacement. Now, if I'm talking gravitational potential energies, and keeping in mind that I need the displacement and the force to be parallel, this object should be moving up or down, which means that my displacement is really a change in height. Remember that Fg, the force of gravity, can be calculated mg delta H, change in height. And that is how we get the potential energy equation. It's just the work done by the internal force of gravity. Okay? If gravity is external, then this work is adding or subtracting from the total mechanical energy. Okay? Big thing to remember with gravitational potential energy is it is path independent. Okay? So it doesn't mean, this is a mountain, it doesn't matter if I climb the mountain like this and get to the top, or if I just straight shot right up, the change in gravitational potential energy is the same. Okay? Yes, I might do more work in the first one, but that work doesn't translate into gravitational potential energy. Okay? A lot of that work likely translates into heat or something like that, or work done against friction, okay, since I have a larger path. Pretty much it with gravitational potential energy. Okay. The other, one last thing with gravitational potential energy is you can set your zero height. So zero height doesn't always need to be the ground. You can set the zero height. So it might be a tabletop, might be something. It doesn't matter, because what we're really talking about is the change in height, not really what the values of the actual height are. So it doesn't matter where you set zero, that change in height is still going to be the same. Okay. Now on to the next one. So the next one we're going to have is elastic or spring potential energy. Potential energy. Okay, which on the reference table, or I usually write as PES, reference table usually writes it as US. Okay, again, it is a potential energy, so it does come from a work done by an internal force. So if a spring is in our system, the potential energy is going to be equal to the work done by the force that the spring exerts. Okay, so that really is going to represent Fs times x. Now I'm leaving a space here because it's important to remember that Fs changes as x changes. Okay, so it's a non-constant force. Unlike gravity, which the force of gravity is pretty much the same near the surface of the Earth. It only really changes when we get super duper high. The spring force, on the other hand, changes as x changes. So we can't just say it's Fs times x. It should really be Fs average times x. So you might be thinking, okay, well, how do I find the average? Well, it's actually really easy. You just do 1/2 Fs. And the spring force x. Remember the spring force is kx. So this becomes 1/2 kx squared. So if you've ever wondered where that equation comes from, that's where it comes from. So K is the spring constant, okay, and it is measured in newtons per meter. It is how stretchy or stiff the spring is. So the larger the spring constant, the larger or the stiffer the spring is. This X represents the change in spring length from equilibrium. Okay. So it's not the length of the spring at a given point, it is the change in length from that equilibrium or rest position. So if I have a spring that its rest length is 0.25 meters, and then I stretch that spring out to 0.75 meters, my X value should be 1/2 meter, since that is the change in length. The last thing I want to talk about in this unit is something we covered, or in this video, is something we covered very quickly in class, and that is power. Now, the reason I went through it pretty quickly is because it's not really tested that often on the AP exam, but I still want to go over it. Okay, so power is defined as the rate of change of energy or the rate at which work is done. So remember, anytime you see this word rate, that means over time. So the rate of change of energy, so that means change in energy over time. Or the rate at which work is done, that means work over time. So power is defined as work over time or change in energy over time. It is measured in watts, just like your light bulbs. So your light bulb, if it's a 60-watt light bulb, that is the power output or how much energy it uses in a given amount of time. That's why the larger the wattage on your light bulb, the brighter it is, because it uses more energy. Okay, we can also measure this in joules per second. Okay. So some consequences of this equation, remember that work is force times distance over time. So we could also say that power is FD over T. And one fun thing to remember is that D over T is actually velocity. So we can say that this is the average force times the velocity, assuming that we are moving at a constant velocity. So this might be like a rock climber climbing up a rock face at a constant velocity, and we could figure out his power output. Okay. One thing that you might be asked to do with power is you might be given a work versus time graph, something like this. Okay, so TSA, the graph. The title is work versus time. Slope is work over time. Area is work times time. The slope of this graph ends up giving us the power. Okay, so if the slope is constant, then that means we are outputting energy at a constant rate. If the slope changes, then that means our power output is changing as time goes on, which might be good, it might be bad. Usually we want things to, output at a nice constant rate. That is it for this energy types and power video. See you soon.